Let us look at the procedural steps in the graphical method for linear programming. The first step is to identify the decision variables. These are generally denoted by x and y. For example, you could say x equals to the quantity of product A and y equals to quantity of product B to be manufactured. The second step is to set up the equation of the objective function. Now the objective function could be either minimization or maximization. A simple example of an objective function could be maximize profits and P is equal to 25x plus 20y. So here P is representing the profit and we are trying to maximize it. And of course x and y are the decision variables. The third step is to set up the equations of the constraints. These equations could be represented as, for example, say 6x plus 4y is less than or equal to 3600, or 2x plus 4y is less than or equal to 2000. The next step is to identify the decision variables on the x and y axis. For example, suppose this is the graph that you're plotting and this is x and this is y. So you have to identify that x is representing product A and y is representing product B. Now the next step, that is the fifth step, is to graph the constraints by reducing them to equality. So we already have identified two constraints, which is 6x plus 4y is less than or equal to 3600 and 2x plus 4y is less than or equal to 2000. Now we have to plot these two equations on the graph. So for ease of plotting, what we would do is that reduce these equations to the sign of equality. So the constraints become 6x plus 4y is equal to 3600 and 2x plus 4y is equal to 2000. So now these two represent the equations of a straight line and it is easy to plot them on the graph. Now to plot them on the graph, we need 2 points on the line which these lines would pass. So the easiest way is to identify the points on the y-axis and the points on the x-axis where these would intersect. So you can put y equals to 0 and that will give you the value of x, and you can put x equal to 0, which will give you the value of y. Repeat the same thing for the second equation and you will get the x and y intercept for these two lines. So once you have identified the x and y intercept, then you can plot the graph. So this is our x-axis, this is y-axis. Take the y-intercept for the first line, take the x-intercept of the first line, and then draw the line. Similarly, for the second equation, take the y-intercept, take the x-intercept, and draw the second constraint. So these would represent your constraints. Now once you have plotted the graph of the constraints, the next step is to identify the feasible solution region. So we have plotted our constraints. Now suppose the first constraint was 6x plus 4y is less than or equal to 3600, and the next constraint was 2x plus 4y is less than or equal to 2000. So now this line represents a sign of equal to. So for less than or equal to, the region for one of the constraints would be the points on the line as well as the points below this line, so this area here. Similarly, for the second constraint also, the points on the line represent 2x plus 4y is equal to 2000, and the points on the line and below the line would represent 2x plus 4y is less than or equal to 2000. So the area which is common to both these constraints would be the feasible solution region for the entire solution. So in this case, this area here represents the feasible solution region. So once we have identified the feasible solution region, the next step is to identify the optimal solution. Now for this, there are two methods. The first method is known as the corner point method. Now this method is based on the fact that the optimal solution lies on one of the corner points of the feasible solution region. So basically, if this is our feasible solution region, let's say this point here A, this point here B, this point here C, and this point here O. These represent the corner points of the feasible solution region. So what this method says is that the optimal solution lies on one of these corner points. So to identify the corner point which is the optimal solution, first what we have to do is to identify coordinates of corner points. So coordinates of, say, point A, since it is on the y-axis, the y coordinate will be 0, and the point here A would be easily identified by looking at the graph. So you can identify the corner points here, x and y. For B, you can either plot the graph like this will give you the y coordinate, and if you put a straight line parallel to y-axis, you will get the x coordinate, or you can solve the two simultaneous equations of this line and this line, because this point lies on the intersection of these two straight lines. So if you solve these two straight lines for the value of x and y, the value of x and y will be the coordinates of the point B. Similarly, for point C, the point C lies on the x-axis, so the x coordinate will be 0, and the y coordinate can be found by the distance from the y-axis. So you can easily find this from the graph. So this will be 0, y. And of course, for point O, the coordinates are 0, 0. So once you have identified the coordinates of these corner points, the second step would be to solve the objective function with the values of x and y for each of the corner points. So solve objective function with each of the corner point values. So the coordinates which give the highest value would be the optimal solution in case of a maximization problem. So highest value of objective function in case of maximization, and lowest value of objective function in case of minimization. These would be the optimal solution. The second step is known as the isoprofit or isocost method. So in the last step, say we have identified the constraints and plotted them, and we have identified the feasible solution region, which is represented by A, B, C, and O. Now in this method, first we have to find the slope of the objective function line and then start plotting a family of parallel lines to each other with this slope, starting from the origin and moving away from the origin. So the first step is to find slope of objective function line and draw a family of parallel lines. So let's say our objective function is p is equal to 25x plus 20y. Now we know that for a standard line, the equation is y is equal to mx plus c, where m is the slope. So let's convert this equation into this format. So let's bring y on one side and everything else on the other side. So 20y is equal to p minus 25x. Let's bring 20 on the other side. So y is equal to p by 20 minus 25 by 20x. So you can divide each of these numbers by 5. So it becomes 5 5s are 25 and 5 4s are 20. So y is equal to p by 20 minus 5 by 4 times x, or this can also be written as y is equal to minus 5 by 4x plus p by 20. So this is the slope. Now what the negative sign means is that this line is moving in downward direction from left to right. So if this is our graph, these lines are like this. It is moving downward when you are drawing it from left to right. So left to right, it is moving downwards. And 5 by 4 means that it moves 5 steps on the vertical side for every 4 steps on the horizontal side. So 1, 2, 3, 4, 5, and 1, 2, 3, and 4. So 4 here, 5 here. So 5 by 4, and you draw this line. So with this information, now we can draw parallel lines to each other which have the slope 5 by 4. Now in this method there are two cases. Say first case is for the maximization objective, and we'll take the second case for the minimization objective. So for maximization, let's say this is the graph and these are the two constraints, and let's say this is the feasible solution region A, B, C, and O. Now we know the slope of this line, so we start drawing these lines in parallel to each other. So let's say first line is this, second is this, third, fourth, fifth, and so on. Now these lines, in case of a maximization objective, are known as the iso-profit lines. So every point on each of these lines will yield the same profit. So please note that each line will yield a different profit, but every point on the same line will yield the same profit. So now in case of the iso-profit lines and in case of maximization, the farthest point from the origin on the feasible solution region which the iso-profit line touches is the point of optimal solution. So in this case we have these lines which are going like this, and so this point B is the farthest point at which this iso-profit line touches the feasible solution region. So this point B represents the optimal solution. Now let's take the case of minimization. Let's say this is our graph and we have constraints like this. Let's say this line has a feasible solution region downwards. This also has downwards. This line has the feasible solution region upwards, and this also represents upwards. So the feasible solution region will be this area here. say A, B, C, D, E. So A, B, C, D, and E would represent the feasible solution region in this case. So again, in this case, once we have identified the feasible solution region and we know the slope of the objective function, we'll start drawing the parallel lines representing the objective function. So let's say this is our first line, this is our second line, this is our third line, and so on. Now in this case, which is a minimization, this line or all these lines, the family of these parallel lines are known as the iso cost lines. Now in case of minimization and iso cost lines, as you keep on drawing these parallel lines to each other representing the objective function, every point on each of these lines represents the same cost. So if you take any one of the lines, any point on this line would represent the same cost. Now since this is a minimization objective, the point which is nearest to the origin on the feasible solution region where the iso cost line touches will represent the optimal solution. So as you keep on drawing these parallel lines, you will find that there will be one line which touches one of the points on the feasible solution region. So say E. E is the nearest point to the origin and is on the feasible solution region, and the objective function line touches it. So this point E is our optimal solution. So this is the first step, that is we find out the slope of the objective function line and draw a family of parallel lines. The second would be to identify the optimal solution point. So once you have identified the optimal solution point, then next step is to identify the coordinates of the optimal solution. So there are two ways to find the coordinates. One is, let's say this is our optimal solution. One is that you can draw parallel lines to x and y axis, and the point where it touches the x axis will be the x coordinate of this point, and the point where it touches the y axis would be the y coordinate of this point. Second option is to solve the two simultaneous equations at which this point lies, and thereby you will get the x and y coordinates. So after you have identified the x and y coordinates, basically you can solve the objective function to find the actual profit or cost. So step number 8 is to calculate the total cost or profit using the optimal solution.